random string leads to one point in this ball. Of course, the decryption algorithm, when it takes any point in this ball, will always map the result to M0. Similarly, the ciphertext M1 will be mapped to a ball, and every time we encrypt M1, we basically output one point in this ball, and these balls have to be disjoint so that the encryption algorithm, when it obtains a point in the ball corresponding to M1, will always output the message M1. In this way, since the encryption algorithm uses randomness, if we encrypt the same message twice, with high probability we'll get different ciphertexts. Unfortunately, this means that the ciphertext necessarily has to be longer than the plaintext, because somehow the randomness that was used to generate the ciphertext is now encoded somehow in the ciphertext. So the ciphertext takes more space. And roughly speaking, the ciphertext size is going to be larger than the plaintext by basically the number of random bits that were used during encryption. So if the plaintexts are very big, if the plaintexts are gigabytes long, the number of random bits is going to be on the order of 128, so maybe this extra space doesn't really matter. But if the plaintexts are very short, maybe they themselves are 128 bits, then adding an extra 128 bits to every ciphertext is going to double the total ciphertext size, and that could be quite expensive. So as I say, randomized encryption is a fine solution, but in some cases it actually introduces quite a bit of cost. So let's look at a simple example. So imagine we have a pseudo-random function that takes inputs in a certain space R, which is going to be called a nonce space, and it outputs in the message space. And now let's define the following randomized encryption scheme. When we want to encrypt a message M, what the encryption algorithm is going to do is first it's going to generate a random R in this nonce space R, and then it's going to output a ciphertext that consists of two components. The first component is going to be this value R, and the second component is going to be an evaluation of the pseudo-random function at the point R, XORed with the message M. And my question to you is this encryption system semantically secure under a chosen plaintext attack? So the correct answer is yes, but only if the nonce space R is large enough so that little r never repeats with very, very high probability. And let's quickly argue why that's true. So first of all, because f is a secure pseudo-random function, we might as well replace it with a truly random function. In other words, this is indistinguishable from the case where we encrypt the message M using a truly random function little f evaluated at the point R and then XORed with M. But since this little r never repeats, every ciphertext uses a different little r, what this means is that the values of f of r are random, uniform, independent strings every time. So every time we encrypt a message, we encrypt it essentially using a new uniform random one-time pad. And since XORing a uniform string with any string simply generates a new uniform string, the resulting ciphertext is distributed as simply two random uniform strings. I'll call them R and R prime. And so both in experiment 0 and in experiment 1, all the attacker gets to see are truly uniform random strings R, R prime. And since in both experiments the attacker is seeing the same distribution, he cannot distinguish the two distributions. And so since security holds completely when we're using a truly random function, it's also going to hold when we're using a pseudo-random function. Okay, so this is a nice example of how we use the fact that a pseudo-random function behaves like a random function to argue security of this particular encryption scheme. Okay, so now we have a nice example of randomized encryption. The other approach to building chosen plaintext secure encryption schemes is what's called nonce-based encryption. Now, in a nonce-based encryption system, the encryption algorithm actually takes 3 inputs rather than 2. As usual, it takes the key and the message, but it also takes an additional input called a nonce. And similarly, the decryption algorithm also takes the nonce as input and then produces the resulting decrypted plaintext. So what is this nonce value n? This nonce is a public value. It does not need to be hidden from the adversary, but the only requirement is that the pair key comma nonce is only used to encrypt a single message. In other words, this pair k comma n must change from message to message. Then there are 2 ways to change it. One way to change it is by choosing a new random key for every message, and the other way is to keep using the same key all the time, but then we must choose a new nonce for every message. And as I said, I want to emphasize again, this nonce need not be secret and it need not be random. The only requirement is the nonce is unique. And in fact, we're going to use this term throughout the course. A nonce for us means a unique value that doesn't repeat. It does not have to be random. So let's look at some examples of choosing a nonce. Well, the simplest option is simply to make the nonce be a counter. So for example, in networking protocol, you can imagine the nonce being a packet counter that's incremented every time a packet is sent by the sender or received by the receiver. This means that the encryptor has to keep state for message to message, namely it has to keep this counter around and increment it after every message is transmitted. Interestingly, if the decryptor actually has the same state, then there's no need to include the nonce in the ciphertext since the nonce is implicit. Let's look at an example. The HTTPS protocol is run over a reliable transport mechanism, which means that packets sent by the sender are assumed to be received in order at the recipient. So if the sender sends packet 5 and then packet 6, the recipient will receive packet number 5 and then packet number 6 in that order. This means that if the sender maintains a packet counter, the recipient can also maintain a packet counter, and the two counters basically increment in sync. In this case, there's no reason to include the nonce in the packets because the nonce is implicit between the two sides. However, in other protocols, for example in IPsec, IPsec is a protocol designed to encrypt the IP layer. The IP layer does not guarantee in-order delivery, and so the sender might send packet number 5 and then packet number 6, but those will be received in reverse order at the recipient. In this case, it's still fine to use a packet counter as a nonce, but now the nonce has to be included in the packet so that the recipient knows which nonce to use to decrypt the received packet. So as I say, nonce-based encryption is a very efficient way to achieve CPA security, and in particular if the nonce is implicit, it doesn't even increase the ciphertext length. Of course, another method to generate a unique nonce is simply to pick the nonce at random, assuming the nonce space is sufficiently large so that with high probability the nonces will never repeat for the life of the key. Now in this case, nonce-based encryption simply reduces to randomized encryption. However, the benefit here is that the sender does not need to maintain any state from message to message. So this is very useful, for example, if encryption happens to take place on multiple devices. For example, I might have both a laptop and a smartphone. They might both use the same key, but in this case, if I required stateful encryption, then my laptop and the smartphone would have to coordinate to make sure that they never reuse the same nonce. Whereas if both of them simply pick nonces at random, they don't need to coordinate because with very high probability, they'll simply never choose the same nonce. Again, assuming the nonce space is big enough. So there are some cases where stateless encryption is quite important, in particular where the same key is used by multiple machines. So I want to define more precisely what security means for nonce-based encryption, and in particular I want to emphasize that the system must remain secure when the nonces are chosen by the adversary. The reason it's important to allow the adversary to choose the nonces is because the adversary can choose which ciphertext it wants to attack. So imagine the nonce happens to be a counter, and it so happens that when the counter hits the value 15, maybe at that point it's easy for the adversary to break semantic security. So the adversary will wait until the 15th packet is sent, and only then he will ask to break semantic security. So when we talk about nonce-based encryption, we generally allow the adversary to choose the nonce, and the system should remain secure even under those settings. So let's define the CPA game in this case. And it's actually very similar to the game before. Basically, the attacker gets to submit pairs of messages, MI0 and MI1. Obviously, they both have to be of the same length. And he gets to supply the nonce. And in response, the adversary is given the encryption of either MI0 or MI1, but using the nonce that the adversary chose. And of course, as usual, the adversary's goal is to tell whether he was given the encryption of the left plaintext or the right plaintext. And as before, the adversary gets to iterate these queries, and he can issue as many queries as he wants. We usually let Q denote the number of queries that the adversary issues. Now, the only restriction, of course, which is crucial, is that although the adversary gets to choose the nonces, he's restricted to choosing distinct nonces. The reason we force him to choose distinct nonces is because that's the requirement in practice. Even if the adversary fools Alice into encrypting multiple messages for him, Alice will never use the same nonce again. As a result, the adversary will never see messages encrypted using the same nonce, and therefore even in the game we require that all the nonces be distinct. And then as usual we say that the system is a nonce-based encryption system that's semantically secure under a chosen plaintext attack if the adversary cannot distinguish experiment 0, where he's given encryptions of the left messages, from experiment 1, where he's given encryption of the right messages. So let's look at an example of a nonce-based encryption system. As before, we have a secure PRF that takes inputs in the nonce space R and outputs strings in the message space M. Now, when a new key is chosen, we're going to reset our counter R to be 0. And now when we encrypt a particular message M, what we'll do is we'll increment our counter R and then encrypt the message M using the pseudorandom function applied to this value R. And as before, the ciphertext is going to contain two components, the current value of the counter and then the one-time pad encryption of the